How's everyone doing? Cool. All right, maybe we can get started. I think today we'll actually be able to catch up. It's going to be a shorter lecture. We are going to modify what we learned about last time, which is that we used reinforcement learning for alignment. We did that reinforcement learning from human feedback process. What we'll do today is to see if we can use RL to build better models, but outside of alignment. So basically what we were talking about a week ago when we talked about how do we do specialization, how do we adapt our models to be better at tasks. We'll do that, but it'll be independent of alignment itself. Okay, so a bunch of logistics before we dive in. I've released the presentation information, so you can find it at that link. There is a Google spreadsheet for sign up. You guys can go ahead, form teams, sign yourselves up. You should be able to access this doc if you log in with your Wisconsin account. And it should be editable. So feel free to jump in. The one thing that you should consider is that if there's a popular paper that multiple groups want to do, first one will get it, so sign up earlier rather than later. The other pieces that we've released homework 2 is due 2 weeks from now. And we'll work on grading homework 1. We expect it's going to take us like another week and a half for that. But I wouldn't be too worried about grades and stuff like that. Any questions about logistics? Have folks been able to form teams? OK, I'm going to assume that everyone has done so or is in that process. Cool. I'll also release the project information. It's going to be something very, very similar, basically, to the presentation information. You can form the same teams or different teams. The only thing you'll have to do is to send me a proposal, which will be due in about a month. OK, so we'll finish up with RL today. We'll start talking about kind of efficiency, which is pretty important for very large models. We'll start with training on Thursday, and then we'll move toward efficient inference next week. All right, before we start, any questions, thoughts? Everybody's happy? Cool. All right, so for today, we'll finish up what we talked about last time. Let's do a quick review of RLHF. And then we'll start doing the stuff that we didn't get a chance to address, which was some variations of RLHF. The most popular one is direct preference optimization, DPO. DPO is kind of the preferred thing to do if you don't have a pretty powerful system. It's very cheap. It's very stable. It doesn't always work quite as well as if you had full RLHF, but it's something that we can do. And then I'll talk about some other techniques that people are working on now. And finally, for kind of the third section, we'll move to this setting of let's avoid alignment. Let's talk about making our model better, and better in the sense of especially reasoning type problems. And we'll see that RL is very helpful there. We'll call this setting RL with verifiable rewards. So we'll see what that means in a second. And then we'll talk about a special loss function that's pretty popular for doing that. It's called GRPO. And then we'll see some examples of what we can do with this and exactly the kind of data sets that it's especially good on. All right, let's start with where we were last time. So let's do a quick review. We said that in general, we can specialize our foundation models for particular tasks. That's kind of been the full story since the beginning of our class. But then we said, hey, for actual human use of things like large language models, and especially chat models, we want these models to speak to humans in a way that they like. And that means responses that are useful, that are helpful, that are phrased in reasonable ways, not having super toxic outputs, things like that. So we said that we're going to make our models do more of that as a special kind of task, and we'll call that process alignment. And we said that this is not something that we can do very easily with just supervised learning, because it's pretty difficult to figure out exactly what the right response should be. So we said it's much easier for humans to say something's good or bad, or to compare responses, than to explicitly specify what is good and encode it in a data set. So the way that we did this is that we said, let's collect a bunch of human feedback. In the simplest form is just comparisons. I prefer one completion or one generation to another. And this is for one particular prompt, but we can run this process many times. I'll start with 1,000 different prompts, run my language model, get a pair of responses, and have humans come and tell me which one of those responses they like better. All right, everybody good with this process? Now notice that there's something supervised learning like about it, right? We do have to collect human judgments. We have to get those preference labels for us to be able to do this process. It is not self-supervised the way our pre-training process was, but that's nothing weird right now, right? Almost all of our fine-tuning is at self-supervised learning, and we do have to get some human signal somewhere. All right, so we're going to do this. Here's kind of the basic setup. We're going to have this overall pipeline. This includes everything that we've talked about so far. The very left column that you see over there, this was the pre-training phase that we talked about. This is indeed self-supervised on tons of data, pretty much all the text out there. So everyone should feel happy with that part. And then we spent a while talking about how to improve these models for particular tasks. This is all within the post-training area. What you're seeing in the second column is just that. We're going to get a bunch of instructions. These instructions have an input, and then there's a human-crafted response that we'd like our language model to produce, and we train on that. So this instruction tuning is supervised fine-tuning. This is kind of the second stage. And why do we need this? Well, we need it because if we want our model to respond to human queries, right, rather than just being an autocomplete, we'll have to do something like this. But the part that we've been talking about, RLHF, is really these last two columns over here. And the first of those second half of these columns is really saying, let's train a separate reward model. And this reward model will now score prompts with their generations, with their outputs, and say, are they high scoring or low scoring? And this is where we actually use this human feedback. We use it to train this reward model that can then tell us, oh yeah, I think this is a high scoring generation, or oh no, I think this is a low scoring, poor generation that we don't want. So this is another language model, but it's no longer a generative model. It does not produce output sentences. It just produces a scalar value, some score, that indicates how good a completion is for a prompt. Okay, so why do we want to bother doing this additional thing? Well, the reason for it is we can plug into our RL pipeline and use it as a reward, and we can essentially tune our entire model to make it more likely to produce high rewards, which is just a standard RL paradigm, but we had to get this reward from somewhere. We had to hook it up to human preferences somehow. So that's why we do this additional step of training the preference model. So these are kind of the 4 steps, really, toward building a ChatGPT clone. You do all of these things, and of course you have to do them really sequentially. You have to pre-train first, or your model doesn't coherently output language. You have to instruction tune, or you can't even do RLHF because the model doesn't respond to instructions. And if you just release the model with the first 2 parts, it'll often be super rude or not helpful. So we'll run RLHF at the end. And if you've done all of these pieces, then really you could release this as a model. The reason why we won't in this class is really we have to get a very large model to be able to have it do coherent language generation. And that's kind of beyond what we have in terms of training resources typically. Of course, if you guys have access to a, 10,000 GPU node, let me know. We can run some experiments for sure. Just a joke. Yeah, everybody comfortable with this overall pipeline? Okay, now, of course, as usual in this class, we're hiding some complexity. In practice, there are many more steps than this. We'll often do stuff between pre-training and post-training. It has a fun name. It's called mid-training. And then there's multiple steps of post-training that we'll run. It's not as simple as just doing RLHF. In fact, RLVR, which we'll talk about soon, is one of those things as well. So the real pipeline is much, much more complex, but it's really just in the flavor of this. You figure out what stage of training you're in, and you get additional capabilities based on what you're doing at that stage. Now, note that these stages can also affect each other. If you do too much RLHF, eventually you can actually forget some of your instruction following abilities and no longer can follow them. So you have to be careful of all these steps. None of them are guaranteed to sort of not damage something that came before. In fact, if you do RLHF and you allow your model to deviate too far from the original model, it can actually forget how to speak altogether. That's why we had that penalty term that prevented it from going too far, that KL divergence regularizer. All right, any questions about this? Anybody confused by what the process is for what we're doing? All right, sounds like we're good. Okay, so let's review what we talked about last time, which was we're going to get a bunch of human feedback. There's nothing super special about this. The easiest thing to do is to fix a bunch of prompts. Now, this is actually pretty non-trivial, right? Because if your prompts don't line up with what the human users are going to ask when you go deploy the system, then your model's not going to figure out how to typically have good preferences, right? It has to have some alignment between what people will do with your model and these prompts that you picked out. So this is, on the one hand, easy. On the other hand, non-trivial to get that representative quality you want. You're going to get multiple outputs for each of those prompts. And really, you can get those multiple outputs in any way you want. You are free to do anything you like here. You don't even have to get them from the model that you yourself are training. You can go to completely different models as well. Now, let's suppose that you get these from a totally different model. What's the downside of doing that? I can do it, right? I can train my own model at home, and I can go ask ChatGPT for a pair of responses to the prompt, and I can get preferences that way, and I can use those preferences for my reward model and run RLHF, right, on my own model. What's the downside of doing something like that? Anyone have any guesses? Go for it.
It's really far from the original model, so you need to train a lot to produce it.
Right. So the problem, of course, is like ChatGPT's responses may be extraordinarily different from what my model will ever produce. So getting preferences on these generations that my model will never get to is not very useful, right? That does nothing for me. My model is not going to be in a position during RLHF to trigger that part of the reward model anyway. So I'll get almost nothing from this because the distribution of generations for my model will be so different from ChatGPT. All right, everybody okay with that? In fact, this will be sort of the biggest and most challenging aspect of all the RL approaches we take, because very often we will run RL with generations that come from some other model that's not the one we're training. And that's called offline RL. And again, if we deviate too far, it becomes very difficult to train. The only thing that we can do is to get more samples, but then we become extremely sample inefficient. OK, so maybe we should be getting the generations from the model we're currently working with. Why is that hard? OK, I'll give you guys a hint for this one. Notice over here that if I was doing that, right, I would have my model. I would create the generations. I would have to go ask the human raters, what do they prefer? I would have to train my reward model. Then I could use it for one step of RL. Then I'd have to start the process all over again. So that's impossible, right? I can't do reward model training on data I've collected in real time during RL training of my original model. That's not tractable. I'm going to have to keep these two pieces separate. Everybody see what I mean by that? This is all happening in a loop, but really I have to fix my reward model, and it's going to be trained on whatever preferences it already saw over whatever generations we initially created. And all we can do is hope to have them be close enough, ideally, to whatever my model is currently producing. All right, let's keep going. So we asked our human rater, which is better. We can do lots of things here. The simplest thing that is really the most standard is just binary output that says I prefer generation 1 to generation 2, or vice versa. Generation 2 is better than generation 1. So this is purely a preference. We're not really stuck with this. We can do anything else we like too. For example, we could actually ask the human rater, here's 5 choices. Go ahead and tell me which ones you like best in order from best to worst. That's fine. That's just a ranking. It's very similar to one of these binary judgments, but it has more information. Unfortunately, it gets harder for humans to actually have a good sense of this. It's easy to say I like movie A better than movie B. It's a lot harder to pick out your ranked list of best 100 movies. That takes quite a long time. So there's some trade-offs over here in terms of what kind of data we can collect. We can also just give kind of scores as a whole. I could tell my human raters, hey, give me on a scale of 1 to 5 how good this quality of this generation is. That's also doable. Unfortunately, humans are not all equally calibrated, right? So some raters are going to have 30% 5s, and some will have 2% 5s. And since you're going to aggregate all these preferences, that becomes a little bit tricky. All right, so we'll stick with this kind of binary output, even though we could do a bunch of stuff. This is no different than when you go and get feedback for whatever thing you see during your day. OK, so we're going to do this second stage of training, which is this reward model. And the thing that this reward model will produce is a score for a generation that has to be consistent with these preferences. So notice that this model itself is not predicting, at least directly, whether generation A is better than B. It's giving a score to generation A and a score to generation B. But we can turn those scores into some probability of one being better than another. So that's how we're going to connect these pieces. We're going to use a preference model, and it's going to have a lot of different forms, but a classical one is the following. It's called the Bradley-Terry model. Sometimes it's called the Bradley-Terry-Luce model. A bunch of people kind of co-invented this at the same time. This thing takes scores and converts them into the probabilities of seeing certain preferences. So the way to think about this is, suppose I take all my favorite NFL teams, I give them each a single scalar score for how good I think they are. All right, everybody okay with that? Now, this score has something to do with whether Team A will beat Team B when they play. But this is not a guarantee, right? If Team A is better than Team B, it'll win more often when they play each other, but they won't always win, right? It's not a binary thing. Everybody agree with this analogy? Okay, so how should we relate the frequency at which Team A beats Team B and connect that to how good Team A and Team B are in terms of these scores? We'll use exactly this model over here, right? The probability Team Y1, which really is a response for us, beats Team Y2, for the same prompt, of course, is given by a function of their scores, and the function, of course, is just softmax again, right? So exp of the score for Team 1 normalized. All right, everybody okay with this? All we're really doing here is saying, yeah, we have these scores that say how good a particular response is, and we want to turn that into the probability of seeing a human preference that's consistent with those scores. Okay, this sounds okay for everybody? Now notice that I've been presenting it the forward way. I'm saying, hey, these scores turn into probability pairs. We're actually going to go the other way, right? We have access to a data set of probability pairs of that type, and we want to learn a model that produces scores consistent with them. That sound good? Okay, so this is just learning a distribution. Really, all I have to do is to parameterize R over there. Now notice that this reward model, it has to have some language capabilities, right? I'm plugging in a prompt X and a response Y. It has to be able to understand those things. It has to be able to say, yeah, Y is a good response to X, which means I can't make this a very simple model. It has to be another language model. But again, it's not a generative model anymore. We'll rip up the language generation layers, and we'll put in there just one head that produces a single scalar value. This track for everybody? Cool. Okay, so we go ahead. We want to train R in such a way that it's consistent with my empirical data set of preference pairs. And notice that my data set is not going to come from a single X, right? It's not like I have thousands of preference pairs for the same prompt. Well, typically I'll have is just a few of them for a single prompt and then many prompts. That's because I want to learn a general model, so I don't want to have the same input each type. Okay, so how will we train R? Well, I mean, just let's do maximum likelihood estimation. That's one simple way of doing it, right? And what does that mean? Well, let's just go ahead and maximize the likelihood. That's the same thing as minimizing the negative likelihood. And for convenience, let's make it the negative log likelihood. And 2 lines of algebra will take us from there to just this simple loss function for our reward model. Now notice this reward model has nothing to do directly with the language model we're aligning. It's a different model. It's auxiliary. It does something different. It has different parameters. These parameters are these psi's over here. This is what we're training at the reward model stage. So we're going to go ahead and optimize this loss function in terms of psi in such a way that on all of our preference pairs, we minimize this guy. I think you kind of tell what's going on here, basically, right? We're saying that we want these two pieces here to reflect how often we're seeing winners and losers for different prompts X. Okay, so this thing is not particularly difficult to optimize, at least compared to a full language model. We can do this fairly easily, and people train lots of reward models out there. You can just fine-tune a pre-existing pre-trained language model. The only real question here are things like, well, what is a data set that you're going to be constructing? Cool. So now we have this reward model. Now we know what to do. We'd like to take our original model, and we'd like to train it in such a way that its generations produce higher rewards. where are the higher rewards measured by? Just this additional reward model that we have over here. In other words, for my original model, which has parameters theta, I'd like to tune those thetas such that the generations I get, when they get plugged into this guy, which is now frozen, our psi, I get a higher score. And that's pretty much it for RLHF. Does the intuition make sense for everybody? Cool. All right. So this is the process that we're going to follow. Now, there's many ways that I could do this, but the setup that we'll use will be basically the most trivial one we can come up with. Within RL, we're going to have state spaces and action spaces. The actions will be just outputting tokens. The state spaces are basically, you can think of them as either as nothing or as here's the tokens I've produced already. So these formulations are all kind of the same, and the reward function is just the thing that we trained right now. OK, the only terminology that we'll need is that what we're doing in RL is trying to get a good policy. A policy is just a mapping that says, given a state, what should I take as my next action in such a way that cumulatively I get good expected rewards. And that's what we're doing here. We're saying, OK, well, given the tokens I've already produced, my policy/language model should take some action, in other words, produce some token, that's going to give me high expected cumulative rewards. Right, sound OK? Maybe the only thing that we've done here is that now we're calling the language model we're training our policy, just to be consistent with RL terminology. And because in RL, the notation that we use for policy is pi, we'll start referring to our language models that we're tuning as pi. That's the only new thing so far. Cool. All right, so now we'll have to actually go and do this process. There's lots of methods for doing it. Typically, it'll be policy gradient based. These are kind of what it sounds like if you haven't taken an RL course. We're going to go ahead and differentiate the policy to get higher rewards. The most popular one is called PPO. And really, there's not too much to it. We'll actually see a bit more today, later on. We're trying to say, hey, give me a good reward in such a way that I'll be able to obtain high values of my train reward function, but I won't deviate too far from my original language model. And that's what you're seeing with this regularization term over here. This is a minus beta, where beta is some hyperparameter, times this KL term that compares the model that we're training right now, pi theta. Theta are these parameters that we're tweaking, to the original model, pi ref. This is usually the base model. This is the language model before we've done this entire process. And again, the reason we're doing this is we don't want to forget all of our model's capabilities, or even our initial ability to speak language. OK, now I haven't really shown over here how we're going to go ahead and maximize this reward function. We'll talk about it in a bit more detail today, especially because we're going to use this in other settings that are just not purely alignment. But this is the basic process. Just go ahead and use your language model inside an RL approach in such a way that you maximize a trained reward model, which we got from human preferences. So a lot of steps, but none of it's super, super complex. Any questions about this? Yeah.
The context of reward model should be greater than or equal to than the final model.
The same, actually, right? Because the context of your original model has to fit both the input and the output generation. And those are the things that are going to get plugged into your reward model as well, right? It has to be able to take in that entire thing and produce a scalar value for it. Cool. All right, so this is the first part. Now, we started talking about why we should do this entire process, right? And it was definitely something different from standard supervised training. And we kind of had this idea of there's a couple of different hypotheses. And one of them had to do with this notion of, well, if we're trying to separate all the possible tasks that we might do with a language model, we can categorize them into kind of 3 overall buckets. And we said one of them is something like perform processing. I give you a bunch of information, and I tell you extract some of it, do something with it, modify it, whatever, right? And all the information the model needs is already there. So in that case, it feels like supervised training should really not have a problem with this, right? It's just a matter of being able to model to have its abilities. Then we also had kind of another version of things, which was generate general creative output. And again, there's less of a problem. You're kind of free to generate whatever you like. It was this middle thing that was more complicated, this idea of knowledge seeking. And one thing over there is that we'd like our model to be able to say no, to refuse things, to say I don't know. And that was something that was much more difficult to address with supervised training. And we spent some time talking about this, but this is kind of where we left off last time. We said, hey, for this case, supervised learning is really going to struggle. Now, if you have a question that you're asking the model, and it really has the answer somewhere in its weights, then maybe this is OK, right? You can do supervised training here, and it's not a big deal. It's just a matter of, did it actually correctly memorize what it was supposed to? The more complicated part for us, though, was the second part, which was, well, if the model doesn't have access to that information currently, what should it be able to do, right? And the ideal thing that we'd like is for it to say, I don't know that information. I can't answer that question. The problem here, though, is that we never actually asked the model to do that during training. In training, there was no credit for saying, I don't know. In training, your loss function goes down for supervised learning when you get things right. And the loss function is high when you're wrong in whatever sense of wrong, whether you're giving the wrong answer or whether you're saying, I don't know. Everybody agree with this logic? Cool. So this is the part that it feels like supervised learning is going to have some general challenges. And really, in fact, we actually kind of encourage the model to lie, right? If the model says, I don't know, that's always the wrong answer. If the model makes a guess that's something else, sometimes it'll get it right. So really, we're telling the model, yeah, you should go ahead and lie. You should go ahead and make up an answer in the hope that you'll actually get it right. You'll get credit for that. Whereas if you say, I don't know, for sure you'll be wrong, at least at the training phase. All right, everybody agree with this? And again, you can try to fix this in various ways, but it's pretty non-trivial, right? Within the model itself, it's not super easy to do this. Of course, you can do things kind of external to it. A few folks have suggested things like you can try to get a calibrated confidence score, for example, for the model. And if that confidence is low, then you can say the model will abstain. But this is external to what the model itself is doing. This would be just an additional harness on it. OK, so what was better when we did things with RL? Well, the one thing that was nice here is that in RL, the kind of credit assignment parts are a bit different. As usual, we get high reward, equivalent to low loss in supervised learning, if the model knows the answer and gets it right. But if the model actually doesn't know the answer, by itself, that may not be that big of a deal, right? Sure, we don't get a reward, but we're not necessarily penalized for saying, I don't know. And even better, one thing that we can additionally do is kind of saying, hey, let's make sure that abstain gets a higher reward than getting the wrong answer. So in other words, we can do kind of three things here. I can craft this reward function that has high reward for correct answer, medium reward for abstain, and then a big negative reward, a bad case for incorrect. And this is very simple, right? There's nothing stopping you from doing this. In fact, within the RL-VR framework that we're going to talk about, we'll do exactly this bit. Everybody OK with this? Also, this is sort of intuitive. When we go test students, right, there are exams where you get full credit for getting the answer right. You get some partial credit or 0 credit for not answering if you don't know. But you get something negative if you answer by guessing and get the wrong answer. So not a very unusual thing to do at all. All right, this makes sense for everybody? All right, so maybe one mechanism for why RL is a good thing in general is this abstain possibility that says, hey, the model is more likely to be able to come out with something like, I'm not sure, I don't know, this question doesn't make sense, all of these other things that we don't typically see in supervised learning. And indeed, you actually see this all the time with models that have undergone RLHF. They will often refuse to answer a question. In fact, that can happen too often, in which case we've kind of too far trained that model. All right, so that's kind of where we left off last time. Let's take a quick break. I can answer any questions folks have. If not, feel free to hang out. Let me go.
Does this somehow break down if you want to use some sort of offline RL where you can this kind of just data set with rewards that does it basically, when you try to do this in an offline manner, does it revert back to the same problems as supervised?
And especially if like the distribution is from whatever policy model you use. And we'll actually see some examples where we're going to give a specific supervisor that is trying to sort of use a so yes, this is not something that but you also have to change it.
So the reward model is important, but it's not just the reward model, it's also the ability to sample the
Yes, exactly. Yeah, that's the issue. And you'll see this would actually come up with the steep people.
Oh, he can't, he's trapped.
Yes. You have no reason to tell them answer. If the model inherently has no confidence that it knows what it's saying, no difference. This is trying to get high. That's not what you know about data sets. There are QA data sets that the model knows nothing about. You can find a good job training those data sets. The model knows on the other hand, the model has high capacity and knows a lot about things that it can actually answer for. It'll just, have same so it figures. There's no way to answer that question without knowing the data set and the model. Well, this is a QA. Here we're not really talking about trading separate reward. We're just talking about, hey, this is getting a reward where it's correct, or it's questioned. And it's incorrect and it's wrong. There's no reward model. Train once, you use it however long you want. Now you're running that for sale list. Maybe all the old recipes are the old recipes. And yes, we have
I guess it's not really saying I can't really read.
we are training the original policy that's being trained or the RO case. And the reward model is used as a signal for it's also a language model. The only thing I've done is I've ripped off the heads that produce tokens, which you use for generation. I've replaced them with a single that produces a single token. The language of the numbers is not
That's the goal.
we don't get anything at all. The only connection is that we're getting a signal from the reward model that we run inside our RO or find the original. Yep, exactly.
He says 20.
Yeah. Oh, that's part of the actual loop for RO. You'll see what the loss function looks like in a little bit. But we run it all and we have this all in the advantage says, oh, if you produce this token, then your reward will be this much better if you get something else. So that's what this means. It's inside this actual training loop. We already always have a token. The question is, okay, for the next token that we're generating in our response, are we doing better compared to being high? And we compute that difference. The difference is very positive, great, we're going in the right direction. Not positive, or it's negative, that we're doing wrong.
Now,
But that's where the information kind of flows. Yes, it's all done on prompts and then responses. We set up this loop with a training loop. The model waits on the thing that's being operated as a kind of whatever the equation is like. Of course, if you want the model to be highly tuned, your strategy, you fix that. And this does this. Yeah, it varies. And also with the function of how much So what's going to happen basically is we're going to start running our organization, and we're going to be looking at a token being reduced in response at like position 5, and therefore at position 6. And at position 5, we're going to compute a term. We're going to call this the equation, and we're going to say, okay, well at position 5, you could have reduced this completely, and the old model covers this way. So now we have to conclusions. One with the we're going to say this was put in one on both those two grids. One was the generation, the other is vector. And that difference is going to be the same. So we're going to say you should tweak your weights in such a way that if this difference is positive, you make it more likely to reduce it. On the other hand, if the difference is negative, you're going the wrong way. You should tweak your weights in such a way that less likely to happen. Yeah. So this is where the gradient is. We're just going to see it as a show of DPO and GRPO losses at the end. So you're going to see it's exactly. Other questions? Yes. Is it like online learning? Yes, sort of, right? It depends on what you consider online learning, which is normally like supervised learning or like a phase of it. What we have here is just a basic RL system. And usually what we'll do, what we don't necessarily have to, is we'll go ahead and kind of generate tokens from the current model, and we'll say, is it beneficial for us to have to produce these tokens compared to our baseline policy, which is our old model? And then this benefit, if it's big, we say, yeah, we should tweak our parameters. They're more likely to produce this token. Or if it's negative, for example, which is bad, you say, okay, like make it so that this is less likely to be produced. So that's kind of how the process works. It's online in the sense that we're generating tokens from our current model, right? But we're not, it's not something that we can run like while we're deploying the system or anything like that.
So, for example, like ChatGPT would give us like 2 responses and then give us like which one will.
Yeah, it's collecting data. It is not learning in real time. It cannot update itself right then and there to make it more likely to do that. It's too expensive for that. Yeah.
If we use like recent numbers, and then if we take like the K, so we are giving it like the same Y, and then bring the K on the same way. What does mean like the regularization from
Oh, yes, but keep in mind that these two models are the same model. Pi ref is the starting point for my model, and pi theta is whatever it is now that I started my training process. Okay, so pi theta is just the model itself during training. Pi ref is the starting point. So this is very much the same model. Now, in the very first step before you start training, we scale from to 0. Okay, the distribution like that. Yep. How do you compare?
Yeah, compare like we were training.
Oh, this is what the Hale term is actually doing. These models are just probability distributions that are conditional on the context we've seen so far. And there's some probability of producing all the tokens in that vocabulary. So this is a distribution, and then I just apply KL in this distribution, like 2 of them.
So it's like compare like the final possibility to
Yeah, so I mean, it's literally saying, oh, okay, well, conditioned on the current X context, the probability of producing this token is 0.001, this one's 0.003. And that's slightly different across these two models, and the KL will directly compute that, right?
So we're comparing like this probability distribution for an X.
It's exactly, that's all the language model is, by the way, right? Like, we're not writing it that way. These are just probabilities, right? What is the probability of the next token considering its chain of tokens I've seen so far? So it's always easy to apply any probabilistic tool on it, like KL.
Like, so we don't need to like consider the entire model, we just only consider like final.
You are considering the entire model, right? But the whole thing just stands for a distribution.
No, like directly considering like the weights, but like.
You mean like we regularize in weight space? We could, right? That's a very standard thing to do. You could say theta minus theta ref, L2 norm regularization on that.
Just too specific.
It's annoying to compute that norm, but that's not terrible in itself. The problem is it's not that easy to relate what the weight changes mean versus like the actual language generation. Like tying those things together is the hard part. Otherwise, computing a norm is, it's a big vector minus another big vector. It's not that bad.
Thank you.
What do you mean? We don't care about the likelihood, right, or field likelihood. We don't care about likelihood. This is something well, actually, empirically, that much. But it's not strange. So what we really have here are a bunch of triplets. And each of these triplets has a y1 and a y2, and we know which one of y1 is better. That's the information. And we use that to essentially no, we don't care about probability of likelihood. First of all, that's what our language model does. I was able to look at this. Right? All the language models are like it's saying you should just know and then you run chain rules to feel like that's not what we're modeling here. All we're going to say is I want to be able to say here is how good this generation is. It's not a conditional probability, it's a quality score. I want my quality scores to work with this generation versus that generation. For this guy right here, right? It's R star at 5.7 per 0.
The accuracy scores were not very good, so
And the way we'll model that is these fruity scores. We'll say, hey, let's attach the score 7 to this generation, the score 10 to this generation. Right? And then once you put here is x plus 7, let's say over x plus 7 plus x plus 8. And that probability would be whatever, close to 0.
So then the
girlfriend is
two
like
statements to the model that calculating.
Once we get to the RL case, there will not be two generations, only one.
There will be one, right?
Yes.
Then we will see the
Yes, and the reward model has two inputs, x and always. No, so here, R itself basically x and y, and that's it. So I can plug in y1, or I can plug in but it's never experience. It's always just one output. And what I'm saying is this overall thing, x with y1, how good is it? And I get some scale. And when I go to R, let's see this. I'm going to say, okay, for the current generation, my model is pretty stable. How good is it? Right? And I plug it into this model. That kind of makes sense. So we're going to get rid of these processes for being shortcuts, right? One and that's just for training this model. For work on itself, that's just one input model. That's a question.
That's funny.
Cool, thank you folks for all the questions. Let's keep going so we don't run out of time. We are going to talk about a couple of variations, and we'll talk about some challenges and kind of like open questions that people have been working on for a while. Let's see some problems for RLHF, And you can kind of guess these because we've been talking about them. But they have a whole bunch of different challenges. And this is a nice paper for discussing like all the different things that you'll see for this. And really all the phases of what we're doing are going to have some difficulties that you have to kind of correct. One is the human feedback itself is actually not that trivial to get right. And then of course in terms of actually obtaining a good reward model, that's a non-trivial process itself. And then finally doing RL as well, obtaining your final policy that has a higher reward, this is also actually pretty difficult. RL systems can be hard to stably train. And this is something that was difficult for quite a long time. People have gotten much better at it over time, but it's still very non-trivial. All right, so let's take all of these in turn and take a look at them. For human feedback, this is the issue that we talked about. I need some sort of representative collection of humans to give me feedback. And they should really, ideally, match up to the users I have for my system. If I'm building ChatGPT, I'll have a set of potential clients, users that use my system. I want to make sure that whoever I get preference labels for RLHF from, they somehow should match up to those users that I have. If my user preferences are totally different from the preference labels I got, then of course I won't have a good model. Everybody agree with that? Cool. So some people are going to have some biases, for example, and that's not always going to line up across different people. The second piece, which is especially annoying, is that when we go and actually get raters, they'll make mistakes, right? Human labeling is an imperfect process. People won't always get everything right. And in fact, there's a classic problem in crowdsourcing of people basically just spamming. If I hire people to say, do you like A better than B, and I pay them by the hour, or I pay them by the number of preferences that they provided, people's immediate action will be, hey, let me just randomly click, right? And then you'll get no information as well, except maybe what the random click distribution looks like. So this is a pretty classic problem for crowdsourcing, and there's sort of tools for how you can solve this as well, but it's still non-trivial. You can also have people who are specifically trying to poison your data, right? This is a general problem for machine learning. People trying to get bad data inside supervised training sets, same basic idea for RLHF. You could have someone who intentionally is picking things that are bad. In fact, you can come up with all kinds of fun scenarios, right? Like corporate sabotage here, right? I can get myself hired to my competitor, and I can essentially always rate responses that speak favorably of my competitor as being very bad, right? They're always losing in preferences. Sounds kind of silly, but people actually do things like this, and it's not that easy to figure it out. Okay, some harder problems, right? In challenging cases, how do you know what's a good output, right? Let's suppose that I have my models output solutions to a very difficult real analysis problem, which I personally don't know how to solve. How should I know which one of the solutions is better than the other? So this is kind of a general problem that we'll run into as we do more reasoning stuff as well. It gets hard to actually even know what is a good response. Okay, the last piece as well is kind of like, it's not super challenging to manipulate people to get the results that you want. So all of these things make this entire data collection and human feedback process pretty difficult as well. Everybody agree? Cool. All right, so we need high quality data. That's another thing that's unfortunately very challenging. As I mentioned, before we do anything else, we have to get our prompts. We'll craft our collection of prompts. From those prompts, we'll have to get our pairwise responses, and then we'll get our preferences for them. Just getting good prompts is actually not very easy. You have to guess beforehand what your users are likely to ask for. And this is actually very difficult in general. So getting a good collection is hard. And of course, having humans craft these for you gets more expensive than asking them just for preferences. So in fact, you maybe have even been recruited by companies that are data vendors. They actually do hire grad students all the time, by the way, if anyone wants a job. And essentially what happens is that they say, hey, I'd like you to craft for me a prompt and the expected response. And they might show you some model responses and ask for a preference label. And for this, they'll pay $50 an hour, $100 an hour, whatever. Very different from just asking people, read response A and B and give me a preference label. That's something that pays almost nothing. All right, so the other piece here too is this feedback quality, right? So we said we're going to use just pairwise feedback. It's very simple, but it doesn't give you everything. You'd ideally like to use very rich feedback, right? I would hopefully, if I could take advantage of it, ask humans to say, hey, what exactly is good about this response? What is bad about this response? How would you fix it? And so forth. But all of those things are both more complex, more difficult to take advantage of, and it's hard to say how you take those and push them into a reward model, for example. So far, we use that Bradley-Terry model for preference pairs to convert these preferences, this binary feedback, into a reward model that produces scalars. If, on the other hand, I get a human to explain exactly what's good and bad about each response, how do I incorporate that feedback into my reward model? Right? We don't have a very simple distribution that we can take advantage of anymore. We'd have to do something much, much more complex. Everybody see what I mean by that? All right, so these are all challenges. There's a lot of different proposed solutions, but they're generally quite complex. Nothing yet has worked very reliably compared to just this basic setup, Bradley-Terry preference pair reward model. Okay, so for the reward model itself, again, this is going to be pretty challenging. Having one universal reward model that can always reliably produce a single score, right, is also very difficult. And the reason for that is pretty simple. I could potentially have responses that are really good on some axis and really poor on some different axis, right? And it becomes pretty hard to say which one of those should dominate the other. It's often context specific. To give you an example, I could have one metric by which I say, hey, these responses are very friendly. Users like the model when it's responding this way. A different one is, how helpful is it? Does the response contain the information the user was looking for? These two things are totally different. If you optimize on friendliness, the model will be very friendly, but it'll never answer your questions. If you optimize purely on helpfulness, you'll get a model that's often pretty rude, but it's always telling you the actual answers you want. So how you kind of combine those, what weights should you put on each, this is pretty non-trivial in general. And of course, it's not something that you can do universally for everybody. Ideally, you'd like to do this at a personal level. Unfortunately, personalizing your model, doing per person RLHF, is going to be very expensive. So that's also not something very easy. All right, the second piece that can be very annoying is that if we're not careful, our reward model might include a bunch of information that really isn't what it's meant to have, right? It might learn that there's some shortcut that always gets to match the human preferences, even though that's not really the point. I'll give you a simple example. When you typically just do vanilla training for a reward model, very often the reward model will give a lot of credit to a long generation. The longer the response, the better the reward model will think it is. Now, why is that, right? Is it inherently true that a long response is better than a short response? Well, the answer is no, right? But it is correlated in a typical data set. Because if you think about what's going on in our preference pairs in our data sets, what we'll often see is something like a very dumb response will be a few words long, and the correct response will be much longer. So that preference pair will always come out as long better than short, even though really there were other factors that were kind of the reasons for those votes. So this is the spurious correlation issue. There's lots of things that are correlated with what's happening, but are not causal, but they get picked up by these reward models because they don't know any better. The reward model can only be trained on these preference pairs. It doesn't have side information about what was the reason the humans picked this over that. And in fact, this was such an issue, this kind of link thing, that for a while, there were like leaderboards with very powerful reward models where people learned all they had to do was to tweak their models to produce longer generations to win. And eventually, their generations were very long, not super coherent, but always came out on top. Of course, eventually, people fixed their reward models, and all of that changed naturally. But it's easy to fall into this trap. OK, the other pieces are still the things that we talked about. What is a good output in general? And we still have this sort of human manipulation issue as well. We can get this actually even kind of from the humans as well. Humans also have issues of not understanding what's the cause of something and using spurious factors as well. All right, and finally, the last piece that I wanted to mention is just training. So the RL component of RLHF, of course, is very difficult on its own. And as you'd expect, just because you've learned a good policy for one environment does not guarantee that it's a good policy in any other environment as well. OK, so I'll briefly talk about one alternative to RL, which gets rid of the RL altogether, but still tries to use this kind of preference idea. It's called direct preference optimization. So this is a very, very, very popular approach. The main reason for this is that it's very cheap. You can run this thing with LoRa on a model of a decent size without too much compute. And what you do here basically is you just kind of take that original reward model that we had, and you push this into the loss function for model training for SFT itself. So rather than using Bradley-Terry for training a reward model and then using that in RL, we just use Bradley-Terry within SFT. And what that ends up looking like is the following. These formulas are getting kind of scary, but they're not really that scary. We have the same thing as kind of before. We have pi theta, the current model we're training with weights that are theta. We have our pi ref. This is our original base model. This is our starting point. We're going to sample x, which is our prompt, from some distribution over prompts. We're going to sample two responses. We'll label the preferred response YW, and YL will be the dispreferred response. This is all coming from our data set, right? So when I say sample, I mean we'll empirically grab these from our data set of prompts and the two responses that we have. OK, now what are we going to train? All that we're really doing here, and you can see is just exactly the same algebraic shape as our log likelihood. We're basically saying, hey, let's make sure that our current model we're training is more likely to produce the winning response compared to the reference model, and less likely to produce the losing response compared to the reference model producing that losing response. That's all that's happening in this loss function, and it's just derived from the Bradley-Terry model again. Yeah, it's basically doing almost nothing. Just try to increase the chances of the current winning generation happening for my model versus the reference. Decrease the chances of outputting your losing generation, again, compared to your reference model. So fairly simple loss function. And again, you just go ahead and do this with, let's say, LoRa. You don't have to do this over all the parameters. You can just go fine tune. You can actually compute the gradient. It's fairly simple, and it has exactly the terms that we talked about. Increase the likelihood of obtaining the winning response. Decrease the chance of seeing the losing response. How much do you multiply these by? Well, basically, the weight is kind of using the reward itself over there, which is implicit. All right, so someone should, or you folks should try to derive this equation. It's not super challenging. It's a very easy process to go run. And people in general will skip RLHF and just do DPO to test out their different alignment approaches. The downside is it doesn't work quite as well. And it turns out all those benefits that we talked about from RL are kind of lost when we go do this. OK, a bunch of different alternatives that we won't have too much time to cover. Check out the survey, which is pretty good. We can do things like AI feedback instead of human feedback. You can think of that as more of a self-training kind of approach if the feedback is coming from the model itself. There are other variants as well. This is a very popular research area. Alignment has several thousand papers generated each time. OK, I'm going to jump into the last part just because we'll run out of time today. Let's move to talking about a different setting, which is verifiable rewards. And really what we're going to do for this is to kind of get outside of the space of alignment. We'll get back to our original problem of let's build a good model for a particular set of tasks. So this is no longer about responses that make humans happy. This is about actually being able to solve some problems, to have good performance on some set of tasks. OK, so the question for us is, can we use RL here as well? Everything we've done so far in these settings has been supervised fine-tuning. We've said, for this input, here is the right output generation. Increase the chances my model produces that generation. Now, we want to not do that. We want to use RL. And let's try to understand what's going on here. OK, so the first question basically is, where is the reward going to come from? For RLHF, the reward was this thing based on human preferences. Increase the chance that you agree with a human that this is better than that. Now we have to use other things. And the other things that we'll end up using are going to be called verifiers. And we'll see that in just a second. Then the second step basically is, where is RL itself and how do we use it? OK, so in general, if we have any kind of ground truth or any knowledge about what a response should contain, we could always use that information inside the reward. right? And the example that we're going to show in a second is, if I have a math problem, ideally, I'd look at the full solution the model generated and kind of figure out whether every step was correct. But on the other hand, if I don't have a way of doing that, if there's a final answer I can just look at and see in the textbook, yeah, is that the right answer? That's still some useful signal, right? I can plug that thing into a reward function. In fact, that's the simplest thing that we could possibly do. Everyone agree? In fact, that's not the only thing I could do. I could put all kinds of stuff in there too. I could say, hey, I'm pretty confident that if my solution is fewer than 3 steps, it's incorrect, right? Give that negative reward. So really, this reward framework, we can do a lot of different things with it potentially. And the place where it's actually super useful is in cases where I do have situations with lots of possible responses, right? That was the big issue with SFT. We were saying, here is the correct response for this input. And we told the model, reproduce that exact response. But really, for that original input, there might have been many different responses that are all equally good. Why should we push our model toward one versus the other? Over here, we're not necessarily going to do that for the same reason that we talked about. If my model gives a correct solution, great, give it a reward. If it gives a different solution that leads to the same answer, that's also great. We're not penalizing it for not matching every single token. Everybody see what I mean by this? All right, we'll work through some examples in just a second. So let's see what these verifiers look like. It's just a basic way of being able to tell, is an answer correct? And by answer, I mean, it doesn't have to match every token of some gold standard response. It's just, do I have something I can check somewhere in there? That checkable element, that's the verifier itself. So let's take a look at math problems, for example, which are sort of the benchmark for this kind of work currently. Here's a problem from a math contest for high schoolers. This one's pretty challenging. It's telling you to do some basic geometric reasoning. And at the end, you express your answer in a particular form, which is there's 2 integers you compute, a and b, and you add them up. Now, for this particular math contest, all of the answers are always integers that are up to 3 digits long. So all the answers are 0, 1 through 999. It's just designed to be that way. So I can have my model go ahead and produce a generation. It did a ton of work, as you can see. It's following all of these different steps. And then it finally comes up with some answer, which is this number in the box over here. Now, for me to figure out whether every step that it did is good is super hard. So we're not going to do that. Instead, we're just going to check its final answer. And we're going to see if this 510 is the correct answer. And if so, we give it a high reward. Or we'll see if it's the wrong answer, and we'll give it no reward in that case. Everybody okay with this? Now again, note the difference between this and SFT. For SFT, I would have a correct proof with all the steps written down in language, and I would compare this entire generation to all of that. And what's the downside? Well, there'll be many disagreements, right? The way I write a solution has a lot of freedom. The only thing that really matters is, are the steps right, and do I get the right final answer? But the exact way I write it can be super varied. So demanding an SFT that I produce exactly the same tokens is essentially somehow being very destructive, right? That's the thing that we're going to sidestep. We're not going to have to do that anymore. We're going to tune our model in such a way that we just say, hey, did you get the answer right? Now, what's another scenario that's actually even better for this RL case? Well, suppose that I actually don't have the full written out solution, just a number. Then I couldn't do SFT at all, right? I could try to SFT against the final number, but that would be hopeless. We know that from chain of thought, there's no chance. So if I actually don't have solutions, I just have the correct answers, then right off the bat, really, this is the technique that I'm going to have to go use. And you might say, well, how could I ever get this right answer without the solution itself? Well, often there's other ways of getting and computing an answer. We just don't have some way of writing the correct solution like this. All right, everybody okay with all these ideas? So this is something that people got very excited about a few years ago, but really started working very well kind of at the beginning of this year. And let's see why. We have these verifiers. Again, they don't have to be quite as simple as just check the right answer, although that's very often the case. One thing you can do, for example, for code, which is another very popular application of this idea, is I can design unit tests, right? And my reward can then just be, hey, did the program that the model output go ahead and actually pass all these unit tests? If it passed all 20, I give it a high reward. If it passed half, I give it a lower reward, and so forth. So this is very standard. And the real motivation for looking at things like code and math is that we have a ton of things out there already. We have a ton of coding tasks that come with unit tests. We have a ton of math problems that come with solutions, and even more of them that come with answers. So the real kind of reason for the explosion in models that do this kind of reasoning tasks is there's a ton of data, so we can do quite a lot of RL with verifiers built on this pre-existing data. So math and code are pretty much the norm, and people are racing to do this for every other kind of reasoning task that you can come up with. I'll show a physics example that I work on at the end. All right, everybody okay with what we're doing here? We're just saying no more RLHF. We don't care about alignment anymore. We just want to make our model good. We're going to make it good at certain tasks. And these are specifically tasks where we can verify an answer, even though the model, of course, will have a longer generation before it produces that answer. And the two examples we've seen are verifiers built on getting the right answer in a math problem, or for code generation, passing unit tests. That's kind of the whole story so far. All right, any questions so far? OK, so what kind of RL should we do here? Well, the first thing we might want to try is let's do exactly the RL that we did for RLHF, but potentially with a new reward function based on these verifiers. So we can go back to our PPO technique, which is the thing that we talked about. This is exactly what we did for RLHF, but we'll have to kind of use verifiers as part of our reward as opposed to using a trained reward model. And by the way, to be clear, we could use a trained reward model as well. That would be convenient for a couple of reasons. One reason is that I don't need to have correct solutions to every problem. A trained reward model could guess whether a solution is good or not. So there are, of course, reward model approaches to here as well. We just won't talk about them until a couple of classes from now. OK, so let's dig a bit further into PPO. We didn't really get into the actual details. Here's kind of what it looks like. This is one very simple version of it. Here's what we're actually going to go ahead and train. Bear with me, the notation is slightly different. Pi theta is still the current policy, the language model we're training. Pi theta old is the old parameters, so similar to pi ref, for example. And what we're going to go ahead and compute is going to be the following. We're going to compute this AT, which is our current advantage, defined in the following way. The advantage is my expected cumulative reward, my Q function, for the current state I'm in, ST, and the current action I'm taking, AT. So this is the token that I've produced of my new model. We're calling it an action, and it's at position T. And we're going to compare what we get from this, compare it to just using our old policy. And that old policy is what this V, the value function, pertains to. So if we didn't do anything, we'd get V of ST. This would be our expected cumulative reward. But because we're taking a particular action, we're producing a particular token, we'll actually get this Q of STAT. And we can compare these two things and say, hey, what did I gain? What I gained is the advantage. Now, the only problem is we don't usually have access to Q and V directly. We'll have to go estimate them. And there's a bunch of different RL techniques for how we do that estimation. But let's suppose that we've run them, and we have our hat AT estimate over there. The next bit that we'll have to do is notice that there's a slight issue here. Everything that we're doing is based still on this pi theta old. But really, we want to be working with pi theta, right, the current model. So we'll just do an importance ratio here. That just kind of weights things correctly. So that's what you see on the left side, nothing super big. And we still have our KL regularization term on the right. That's the same idea of not taking steps that are too big. So this is the more detailed version of what we talked about already. There's an additional variant that people often do. This is to sort of control, in a different way, how aggressive the steps we take are. It's based on clipping. Really, it's just saying, like, hey, if the advantage is too big, control it. Don't permit it to get too big or too small. Clip it in some range. Now, this is very kind of standard. People actually often do both these things simultaneously, But this is really the loss function that's being optimized in PPO itself, including for RLHF. And notice again that the advantage is really going to include rewards. So when we use our trained reward model, we're going to say, yeah, what do you get from using the current token versus using the old policy token? That's going to be the advantage in that case. OK, so far we haven't done anything. But as you can see, this is something that we can do for RL with verifiers as well, as long as the advantage reflects something about our verifiers. Everything else stays the same. We're still outputting tokens in such a way that we increase our advantage. In other words, we increase our reward. We just have a different notion of reward that we'll have to filter in. Everybody OK with this so far? We're spending 2 minutes on this. The RL class next door will have 2 or 3 lectures on it, so bear with me a little bit. The details are not critical. We just need to understand kind of how we're using rewards in different ways. OK, so now we're going to swap one thing in a way that's actually quite powerful for using verifiers. And it's a very popular loss function called grpo. OK, so let's see what it does. This was introduced in all the DeepSeek models, basically. Here's the full loss. It looks slightly scary, but it's actually almost exactly what we saw before. Notice that we still have importance sampling times AI, or advantage. And notice a further thing that we're using the clipping. And finally, we still have our KL regularizer term. So actually, everything you're seeing here on the interior, inside that summation sign, has not really changed from PPO, or at least not at first glance. The only thing that we'll really do here differently is rather than saying, here's an input and here's a response, we're actually going to sample multiple responses, a whole group of them. And what we'll do with them is that we'll compute an advantage over them. And specifically, we'll make the advantage relative to all of the scores that we got. So we'll go ahead and say the advantage AI for the IF solution that we generate for the same problem, the same prompt, we'll normalize it. So subtract the mean of all of the rewards for the whole group of answers and standardize. And now we have a bunch of advantages for each of these terms. Let's understand where we get these RIs, because we're almost done with this whole thing. The only thing that's going to happen for these rewards is going to be 2 things. The first thing is, did this solution get the right answer in my problem? That's an accuracy reward. It's exactly the thing that we talked about. Did you answer the math problem with the correct number? So it's a 1 or a 0, and that's all you get. Then the second bit is something about formatting, which is, did the model use a special token about thinking? In other words, did the model actually spend time going step by step and solving the problem rather than guessing an answer? Now notice you kind of need something like both these things. If you always just guess the right answer, that's not super interesting, because maybe you don't have good solutions leading up to it. If you just have these formats, then the model doesn't have to actually get the right answer. It'll just pretend to be thinking. So this simple combination will go inside our reward. Those rewards will go inside our advantage, but per group. And the model will kind of figure out, oh, yeah, I should be pushing the response that is getting the highest reward relative to the others in the group. And that's basically it. It's an extremely simple formulation. At the core of it is just, hey, sample many solutions, check their answers, and make the model much more likely to produce the one that's getting the right answer. Now, quick question for you guys before we wrap up, because we're almost out of time. Let's suppose that every single solution that I generated is wrong. They all have accuracy 0 reward. What can my model learn from that? Yeah, I've heard some people saying it. The answer is nothing, right? I mean, maybe you're lucky with the formatting stuff, but really not much, right? So as you can see, what we want here is to find problems where the model doesn't always get them right. In that case, there's nothing to do. Doesn't always get them wrong. Then there's no signal. But it's somewhere in between, right? If we have a group of 20, 1 or 2 of those solutions are right, the others are wrong, that's perfect. We'll be able to push toward the correct solution. And that's kind of all that's happening in grpo. But this is actually something so powerful that it led to an open source model, which is not very big, to perform at the level of 01, 03 closed source models that were the first ones to actually do this kind of reasoning. All right, so we're out of time. We'll talk more about this next time. A very powerful idea based on something very simple. Thanks, folks.